Hello everyone. In this tutorial we are going to explore eigenvalues, eigenvectors and diagonalization in Python using the NumPy library. So I will go through 10 examples starting from the basics and then move on with more advanced examples. So let's get started. In the first example we will take a simple 2 by 2 matrix and use NumPy's eigenvalue function to find its eigenvalues and eigenvectors. The function returns both eigenvalues as a list and eigenvectors as columns of a matrix. So here is our example. We call the function and then do some print statements to verify the result output. And if I run it, we can see this is our matrix A, and then the eigenvalues are 5 and 2, and then we have the eigenvectors that is calculated for us. Now let's look at our second example. Next we will verify that for each eigenpair the equation A times V equals lambda times V, which is the eigenvectors, actually holds true. So we want to verify this. This shows that the eigenvector truly scales by its corresponding eigenvalue when multiplied by the matrix. So we can run our second example. So we can see that A times V must be equal to lambda times V, which is our eigenvalue problem. So actually we are just verifying in this second example that the eigenvalues and eigenvectors that we obtained are indeed satisfying the eigenvalue problem. So it's a nice example to just demonstrate that our answer is actually correct. Look at a symmetric matrix, a 3 by 3 matrix. And one special property of symmetric matrices is that their eigenvalues are always real and their eigenvectors are orthogonal to each other. And we can easily check this in Python. Here you see that we use a slightly different function, eigenvalue, and we have this h function. This is another function in linear algebra that guarantees real eigenvalues and orthogonal eigenvectors. So if you are dealing with a symmetric matrix, it is better to use this function. And we can print the function, the eigenvalues that are calculated and the eigenvectors. And we want to check, because this is a symmetric matrix, as we said, the eigenvalues must be all real. And we also should satisfy this orthogonality condition. And in order to check this orthogonality condition, we are going to compare basically a 3 by 3 identity matrix with the multiplication of these two matrices where we take the transpose. So we have a transpose operation and then we are multiplying the other matrix V, which we have already calculated as the Vex matrix here that contains the eigenvectors. And we will just verify if these two are the same. If this is really equal to the identity matrix, this is going to return true if the orthogonality condition is satisfied. And here, just to remind you, here orthonormal, when we say orthonormality, we are talking about, we have the orthogonality condition and we have the normality. And normality refers to having a unit length. And that's why we have this identity on the right-hand side. We are checking this. And optionally, you can also verify our eigenvalue problem is satisfied for each eigenpair that is calculated. And we can do this in a for loop. So this is just a little bit of an extra code here, where we calculate the left side of the equation and right-hand side of the equation by performing these multiplication of these. And then we can just print on the screen and verify that these two are just the same. So let's run it. Here we see our eigenvectors are orthogonal. Yes, that's verified. And then we can also verify the left side and right-hand side for the first eigenpair. This is in a for loop. We are running this. So we verify that every time actually the eigenvalue problem is satisfied. So this completes our example. Now let's look at example 4. If a matrix has enough linearly independent eigenvectors, we can diagonalize it. That means we can write A equals P times D times P inverse, where this matrix D is a diagonal matrix of eigenvalues. So we can calculate and reconstruct our original matrix to verify again this linear algebra relationship. We can run this. Here is our matrix A that's printed on the screen, and then the diagonal matrix, which contains the eigenvalues, as we said, are 6 and 1. These are the eigenvalues. And then we can reconstruct this matrix A by doing this linear algebra operation. So we have our matrix P, which is containing the eigenvectors. And then we take the inverse of this. As you see, we have the inverse of P, and then we make this matrix multiplication. We have these three matrices, and we should get back the original matrix A that we started. And here is the verification. So this completes our verification, and indeed the operations are correct. 5. Once we have the diagonal form, computing powers of a matrix becomes super easy. For example, A squared can be written as P times the diagonal matrix D squared times P inverse. So we can compare this result to normal matrix multiplication, and we can again do a confirmation. And in the first example here, for example 5, we have A squared that's calculated from taking the squares of the eigenvalues. So we are taking these squares, and then we do the multiplication with P, which is the eigenvector matrix, and then this is the inverse of the eigenvector matrix. And you can also compare this with the direct multiplication and taking the square of A squared, and we can verify in the first part here. You see both of them gave us the same result. Now let's look at the example 6. Raising a matrix to the 5th power. We can extend this idea further and compute A to the power of 5 instead of multiplying A 5 times, which is not convenient. We just raise each eigenvalue to the 5th power, and that will actually simplify our job. So for example here, taking the 5th power of A, we are actually just taking these eigenvalues to the 5th power, and then still the rest remains the same. We have the P times P inverse here, and then we can print this, but if you want to compare and multiply A 5 times, and you can also verify the result as we did in example 5. So it's a very similar example, and you see this is the 5th power of A using the diagonalization that we obtained. Now in example 7, different from the previous ones, we have complex eigenvalues. So you see that we are given a matrix C, which is 0, -1, 1, and 7. And then we just usually use the eigenvalue or eigenvalue H functions. And here it's not symmetric, so we can use the regular eigenvalue function as we did. And if you run as usual, we can just print these on the screen and verify what we obtained. So we have the complex, as you see, we have the complex numbers. We have plus 1j and minus 1j, that's the eigenvalues. That's the conjugate of the complex eigenvalue here. So it is represented as minus 1 times j. And the corresponding eigenvectors are also just printed on the screen, which are also complex. Next example, we have repeated eigenvalues. This is another case. And here we have a 2 by 2 matrix. One more time, we can use the eigen function to obtain the eigenvalues and eigenvectors of this matrix. And then we can check the rank of this eigenvectors matrix, which will show us that actually the number of independent eigenvectors is just going to be equal to 1. So that's not sufficient to obtain the diagonalization of a matrix. So we are not always able to diagonalize. So the condition is we should have a sufficient number of linearly independent eigenvectors So we can actually diagonalize our original matrix that is given here as D. Now, let's look at the example 9. And here we are diagonalizing a 3 by 3 matrix this time. This is matrix E. And then we use the eigenvalue function. And then we diagonalize our eigenvalues and write this as matrix D. And then again we are verifying our relationship. And we have the matrix of eigenvectors. And then this is the inverse of that. And this is the matrix of eigenvalues on the diagonal. And when we do this multiplication, we can just verify that we can reconstruct this original matrix E. And if you run it, we can simply verify here. And indeed, we obtained and reconstructed the original matrix E. Example 10, here we want to check the stability. And we use the eigenvalues most of the time in real-world context, and these appear in dynamical systems. The eigenvalues of a transition matrix tell us about the system stability. If all eigenvalues have magnitudes less than 1, the system is called as stable. And we can check that using our example here, which is again a 2 by 2 case, and we have the matrix F. We calculate the eigenvalues and we just print them on the screen, and we are just making this stability check, and if the eigenvalues are all less than 1, then we are going to call our system as stable, and this will be equal to true if this condition is satisfied. So for our example here, if you just run it, you can see that the eigenvalues are less than 1, so we call this as a stable system. So that's all. We have learned how to calculate eigenvalues, eigenvectors, verify their relationships, perform diagonalization, compute matrix powers, and even check stability using eigenvalues. I hope this gives you a clear understanding on how powerful eigenvalue decomposition can be in linear algebra and in your future applications. Thank you for watching.